Good morning, everyone. This is the first segment for section 7.4, and I just want to take a minute to talk about the next two sections. So in both 7.4 and 7.5, we developed the idea of a vector, which in some sense is kind of a two-dimensional or higher dimensional type of number. There are many different kinds of things that fall into the category of a vector. But what we're going to talk about is one very specific kind, which if for any of you who have ever taken a physics class that involved more than one dimension, you may have been introduced to this idea. But basically, the notion is that there are a lot of physical quantities that cannot solely be described by their magnitude. They also need some kind of a direction associated with them. And usually the way I think about, how to approach that with a class is to say, all right, if I'm here in Kansas City, and I decide to walk for 50 miles, the question might be, where am I at the end of it? And of course, that question is not answerable other than to say I'm within 50 miles of Kansas City. You can't really pin down exactly where on the planet I am, even if you knew precisely where I started. So that idea that we need both a length or a magnitude in the sense, and usually it's easier to understand these with lengths and direction, but we can of course extrapolate that up to speed and direction or any other number of physical quantities that require a direction in some sense to make a clearer sense of them. So that's kind of what we're developing. We don't use a whole lot of applications because you're going to see that kind of stuff in a like a Physics 130 or higher here at Longview or MCC. And if that's a class that you have to take, or if you have to take a statics course, applied statics course, this development of vectors is essential to that. In the past, I used to kind of defer the class. Defer this material to a physics class, maybe just introduce it in the context of complex numbers, which is material that is covered in chapter 8, which we don't cover anymore. But it seems as though the curriculum, the folks that have sort of given us, have gently suggested the trigonometry curriculum have suggested that this is an excellent place to introduce these ideas. So what I'm going to try to do first is I'm going to approach this from a mathematical context. We want to consider a number that has both a length and a direction. And by length, I mean, we could be talking about vector. We could be talking about velocities. We could be talking about accelerations. We could be talking about any number of things where there is a magnitude. So that length really gets associated with magnitude. And then we have a direction of some kind. We won't do anything above 2 dimensions because it's not necessary for us, but understand we live in a 3-dimensional world, and this is the step into that bigger world. So we're going to introduce this idea of an arrow vector. And what I'm going to try to do from a mathematical context is show you how an arrow vector works a lot like maybe say the field of real numbers, but there are some subtle differences. So without any more here, I'm going to shift over to the document camera. Hopefully it's still in pretty good position. It's been a couple days since I was doing any videos, but not too bad. Just do a little bit of adjustment here. Okay, so just a little bit of adjustment. All right, so this is going to be section 7.4, page 1. I don't like this marker. It's already kind of a little dead. So consider then if we had some kind of an arrow where there's a preferred kind of beginning point and an end point. This is called the arrow at the arrowhead, if you will, is called the tip. And the tail, these are kind of colloquial terms, but we'll use them quite frequently as we talk about this. So the arrow represents a quantity of some kind that requires both a magnitude and a direction. Now, certain types of physically measured quantities would never require this, like, for example, say mass, well, time might, but time is still a one-dimensional sort of thing. It's either positive or negative, but something that operates in at least 2 dimensions. So what we can do is we can put an artificial coordinate system on top of these arrows, but they have no position in space. They're kind of like when we were first talking about angles, and this is their connection to trigonometry. In fact, we had said that, you know, it's an amorphous sort of object that's sitting in space until we put it on top of until we put a coordinate system in place. So we can rotate, we can do all kinds of interesting things, and the math should still work out the same. So when we are describing vectors, we usually use variables of one kind or another rather than draw pictures of them every time. And so the sort of standard is to use a bold-faced letter, like especially the letters U, V, and W are used pretty U, V, and W are used pretty commonly for vectors to distinguish them from X, Y, and Z, which are used predominantly for coordinates. But we can't really generally do a bold kind of representation on a piece of paper. And so typical notation will be U with a little hat on it, or maybe V with a little hat on it, or W with a little hat on it. These are almost universally recognized to be vector quantities, and so you have to start thinking about them in a different way. And they're always lowercase, because there's another thing that perhaps you'll see, or you have seen before in college algebra, called a matrix, which actually is a function that will operate on these vectors. Generally matrices are given bold letters, but they're always capital letters, so that you'll see things like capital A or capital B or capital C, which are matrices which operate on vectors. So anyways, not to repeat myself, we're only really concerned about these little arrows at this point. And maybe at some point in the future, you'll have a chance to see how these work in a bigger context. So the first thing we'd like to do with any kind of a mathematical system is we want to verify some properties of what happens here. I mean, so how can we manipulate these things? Well, how can we manipulate these things? Well, there's 2 different ways that we're going to look at where we can do things to vectors. We're going to look at the operation of maybe, say, multiplying by a regular number. So this is usually what's called multiplication by a scalar. And I'm trying to make sure that the book, but I use kind of similar notation to what the book doesn't actually use a variable. Yeah, it does, K. Okay, so let's say that K is some real number, just like the number 2 or 1.5 or something. Whereas these vectors are kind of refer back to this picture. This is just a regular number, just like you know. So the first thing we'll look at is scalar multiplication. Like, what does it do if I multiply these together, and how do I add 2 vectors together? So like, say, U plus V. And it turns out that they're kind of closely related. And it is relatively intuitive. So maybe by talking about what plus means in the context of maybe just a vector plus itself first, where basically K is 2, that might make sense. So when we talk about addition of vectors, if we're looking at the drawing, how we draw them, what we do is we take a vector, whatever that vector happens to be. Let's call this vector U, and we go tip to tail. So whatever, this would be U, and then if we want to add another U to it, this whole arrow becomes U plus U, so that this now becomes a sort of longer vector, becomes U plus U, kind of loses the tip in the middle, or you might actually call that 2 times U. And so this gives us some insight as to how to multiply by a scalar, right? So, and usually when it comes to this material, I would go back and forth with the students quite a bit and say, so what do you think happens when you do this? What happens when you do that? sort of the two things that we'd like to look at is what does multiplying by a negative number do, and what does multiplication by 0 do? So 0 should be pretty obvious, right? If you have this is how we do it with a whole number, right? Just add little different pieces. What would it mean to multiply by 0? Well, you have 0 of them. Okay, so any vector times 0, so 0 times any vector just simply equals what we call the 0 vector, which is very boring. It's just a point in space, right? It has no length, and so therefore it really has no direction either. So multiplication by 0, pretty simple to do. What about multiplication by a negative number? If this is addition, can we conceive of a way to do subtraction? So what would, say, minus u look like? Well, minus u turns out to be just like u, except in the opposite direction. So it's the same length, just 180 degrees off, right? And this is not to say subtraction. What this is really saying is this is -1 times u, right? So that if you had -2 times u, it'd be the sort of the reverse of this thing up here. And that way, what we end up with is a system that allows you to produce the 0 vector in a way that makes sense. So that, for example, if you had 2u plus -2 times u, you would expect this to equal 0 times u, which is the 0 vector. We have to think of it in terms of how you're adding these, what addition really means, which is to do things tip to tail. So kind of in a sort of over here to the side, here's 2u, and then if I lay this on top of it, which I'm going to do it kind of off to the side, but then kind of coming back, minus 2u, the total of these is just going to be the 0 vector, so dot, because we come right back to where we started from. And so this kind of is consistent with the way that algebra works. If we kind of collect the scalar numbers together and perform an algebraic operation on them, we end up with u times 0, or the 0 vector. Okay. So this is just kind of a small scale picture, just thinking about one single vector u, whatever it happens to be. So what would we do in a situation where maybe we have 2 vectors? Well, it's the same kind of plan. We're just going to put things tip to tail, as much as we need. So if we imagine now that we have, here's maybe the u vector, and here's a v vector, right? What does it mean to have these added? Well, if we go a plus v, so we start with, u plus v, we start with u, which is the first one on the left of that equation. So we've got, this is what I'm trying to do here, is u plus v. So here's u plus v. So I start with u, and then I tack on v after the fact. Probably shouldn't have put that right there, because this long vector here becomes u plus v. So we have u, v. The net result is you start from the tip of the first one and go to the tail of the second one. And so the net result is that u plus v looks something like this. Okay? Now, this begs the question, though, is addition of vectors commutative? Does it matter which order you put them in? Well, I don't know. Let's take a look here. Let's try it in reverse. So let's start with v, and then add u to it. So v plus u now. This one is v plus u. And notice it's going to, when we kind of extract it out, it's going to look identical. And the reason this is because of geometry, right? What you're creating here is kind of what's called a parallelogram, and that's actually one of the words that's used in this context. Is it's like, notice if we were to sort of draw just a geometric shape all by itself, that here's here's u. Here's v, here's v again, and then there's u. So if this is kind of where we started from, here we have u, v, u, v, just kind of in the opposite order. So u plus v becomes this diagonal, and v plus u becomes this diagonal as well. So one thing that we know about vectors, just by the way that we actually add them up, is that they are commutative. So u plus v equals v plus u. It's a nice result, but not exactly useful for what we're wanting to do. The question really becomes, how can we like come up with, like, in a numerical sense, not a graphical sense, because using graphing to try to try to do mathematics is extraordinarily challenging. So much like what we did with angles in chapter 1, we're going to take this information and we're going to build up into a system whereby we can sort of numerically calculate these additions. But as it stands right now, it feels like my video is getting a little long here, and rather than push on into different representations of vectors, but the next step will be to say, okay, here's this sort of graphical idea, and now let's turn it into something where we can crunch some numbers and come up with a cohesive way of thinking about these things. We are going to put them on a coordinate system, an arbitrary one, just like we did with angles. But then we're going to find that there's a certain preferred way to be able to add and subtract these things. That's actually pretty slick, but not particularly useful in terms of maybe the quantities themselves. So I will be back here shortly, and good luck.